In this short video, we'll look at how to calculate crack widths in reinforced concrete structures. This is one of several videos on the control of cracking for reinforced concrete structures that come from the book Structural Design from First Principles. Solar gain is a temperature rise due to sunshine, and the resulting expansions are a cause for cracking. So you can see in this situation we've got a cross section through a building here, and thermal expansion of the roof slab is causing the roof slab to expand, and that's pushing the columns outwards, and we're getting a bending moment developed at the top and at the bottom of the columns. In this particular situation, the bending strength of the beams supporting the slab is higher than the bending strength of the columns, so most of the movement is taking place in the columns. It's easy to work out the amount of expansion that we would expect. It's simply the coefficient of thermal expansion for the concrete, which is typically 12 microstrain per degree centigrade, multiplied by the change in temperature due to the solar gain, multiplied by the length. So if we expect the expansion to be equal on both sides of the centre line of this building, then L is simply half the length of the building. So moving on to a worked example, what we're going to look now is the cracking on the top floor of a building due to the expansion of the roof. So a roof of a hotel heats up and expands, causing the edge columns to move sideways by 20 millimeters, as illustrated in the figure you can see here. The story to story height L is 4 meters, and the columns are 400 millimeters wide and 400 millimeters across, so 400 by 400 square with 25 millimeter cover, and each is reinforced with 4 25 millimeter rebars and 12 millimeter diameter shear links. The stiffness of the columns is far less than the stiffness of the beams, because the beams are deeper than the columns. Therefore, the supports can be assumed to be clamped. And so we can idealize this as a beam that's built in at the supports with a sideways movement. And this situation is well covered in lots of textbooks that tell you how to work out the reactions and moments. So the equation for the end moments for this situation, which is found in many different formulae tables, is 6 EI delta, where delta is the translation movement, divided by L squared. And this will cause tension cracks to form on this side and tension cracks to form on this side. So we know that the moment is equal to the stress divided by Y times I. So combining these two equations, we can formulate this equation here, which is the strain is 6 times the movement delta, which in this case is 20 millimeters, times Y, which is the distance from the neutral axis to the point you're interested in, which we're going to take as half the width of the column, divided by L squared. So we're expecting a 20 millimeter movement to result in a strain of 1,500. So the next step is to calculate the area of the tension zone in the beam, which you can see in this figure, which is the area hatched. The effective depth in this particular column is 350.5 millimeters, which is calculated here. So that gives us an area of the tension zone of 2.5 times 400 minus 350.5 gives us a tension area of 49500 millimeters squared. The reinforcement ratio is just the area of steel within this zone divided by the area of the tension zone. And then from the Eurocode 2 expression for beams, the crack spacing is 3.4 times the cover, 25 mil, plus 0.17 times the rebar diameter, 25, divided by the reinforcement ratio, so 300 millimeters. And so the crack width is the strain, which we calculated earlier, of 1500 microstrain multiplied by 300. So we're expecting solar induced movement to cause a crack width of 0.45 millimeters, which would be considered a problem. That would be excessive cracking, and we would need to redesign this to reduce that crack width. I hope you enjoyed this short video on the control of cracking in reinforced concrete. There are 6 more videos on this topic available on YouTube and also in the book Structural Design from First Principles. I hope you enjoyed this, and do press like if you found it useful. Thank you.